So please, Henry, the floor is yours.
Thank you. So for welcome at my presentation, our presentation. So Derek, where are you, Derek? Oh, there, over there. We will do it together. He will show you some slides about the Ostara project, Ostara installation, and also the crystal green. And for those who were also in the morning session, I have some new slides. So don't fall asleep before we will end up. Oh, I can see it there. The live project Omzet Amersfoort, a strange Dutch word, but it's just an energy and resource factory, like more in the Netherlands. Just for those from abroad who do not know where Amersfoort is, so in the Netherlands we have 22 waterboards, and we are in the middle as Vallei and Veluwe, and Amersfoort is in our region on the west side. And at this part of the region we treat the sludge and the wastewater in Amersfoort. So this is the installation where we are at the moment, and later on we will show more about this. I want to share some things about the history of the project, and also about the energy and resource factory, of course, and some future plans after we have seen the Pearl reactor from Derek. So we started 8 years ago thinking about a plant who would not only treat wastewater but would also produce a lot of energy and also nutrients. And a nice thing in the Netherlands was that we had the shared project energy factories with all the Dutch waterboards together, which shared all the information to learn from each other. So that was the reason why we were able to build this this plant rather fast, although it took 8 years before today to realize it. At the same time, we were thinking together about resources from wastewater. Yeah, I'm sorry, Merle, that I have to use the word wastewater. I'll try to change it, but we also talk about sewage and sewage, and I'll try to tell some failures, but I don't know if I'm able to. So in the roadmap for wastewater 2030, we thought about what are all the possibilities for the waterboards to share their wastewater and all the resources from the sewage with neighbors, like the industry, like the farmers, like the cities. And we're still working on that. But that inspired us also to think about recovery of phosphorus and nutrients and other products. So we, before we started this project, we were already thinking about how to make the plant more energy efficient. And one of the measures we took was the biogas filtration that increases the amount of, let's say, energy produced, electricity produced from the biogas. But also more up hours for our combined heat and power plants, so more production of energy. We started to change our surface aeration for bubble aeration to improve the energy efficiency by 30%. We built a deammonification reactor for the treatment of centrate. Also for the reason that we don't have to build a third line for wastewater treatment, but also for energy reasons. And in between we also built a sand filtration installation, increasing the amount of energy consumption of the plant, but at that time we already realized that we have to ask the market parties who wanted to build this to think about energy. And we were able to decrease the amount of energy for the sand filtration installation to remove extra phosphorus by a factor 10. So we have built 7 installations, and the first one had a factor 10 higher energy consumption as this one in Amersfoort. So all measures to reduce the amount of energy produced, and just by doing the simple things, we increased the energy consumption to production rate from, or the other way around, production to consumption rate from 30% in 2006 to 60% in 2012. And here I show some measures in the graph. I'll not go in detail, but you can see that in 2006, in the red line, we produced about 30% from the blue line, and in 2012, we produced almost half of the amount we consumed. So then after that, we started, or let's say in between, we started with the project Energy and Resource Factory. And we defined 3 phases for that. The first one was just improving the amount of energy production by building a central digestion for 4 treatment plants in this neighborhood, the thermal hydrolysis, and a new combined heat and power plants. The second phase we want to realize was the biological pee removal and the phosphorus recovery to produce the struvite, or the fertilizer, but also to reduce the amount of chemicals used for phosphorus removal. The third phase, and this has still to be realized, was the drying of sludge with the excess heat we have here in Amersfoort. We had hoped to realize this already now, but because of the complexity of the project, we weren't able to do so. So now we move to our treatment plant in Ede, where we have a pilot on treating sludge, drying sludge with excess heat. And if this will be successful, we will implement it in Amersfoort also, making the treatment plant even more energy positive, from about 100 to 150%. So what we expected already talked about, it is in the first phase to make the plant energy positive, but also, and that's the improvement of the sludge dry weight of our sludge, also important for the business case for the whole installation. The second phase was the recovery of phosphorus. We hope to produce 900 tons a year in the near future. And now probably that's one of the points we learned in between. It will take some time because before all the processes at the plant will be together producing this. For example, if you nowadays we bring a lot of phosphorus back into the treatment line in the water treatment, and therefore we are not able to optimize the biological phosphorus removal. Since a few months we removed this phosphorus by the Phosphorus Reactor, and now we can improve the biological phosphorus removal. But that will take some time, I guess half a year or so. For the LIFE project, we promised to be ready in 2016, and that's one of the reasons that it will take some more time to realize that. Actually, we could have known, but as always, we forgot something. And we also want to reduce the chemical consumption, and we hope to earn this back in 6 to 7 years, and we still expect that today. And the third phase, we hope to produce sludge, which is 90% dry weight, and then we calculated we could dry about 75% of our sludge. But now, today we are producing so much biogas that I hope we will be able to dry all the sludge in the future. So this is how the plant looks like now. I'll later come back on it, what are the different parts. Then I move on to the process scheme. I have 3 slides. One is about the sludge line. As you can see, this is the region of Amersfoort with treatment plants in Soest, Nijkerk, Woudenberg also. And all these sludge is coming to... First I have to tell, we also introduced the wash strip process to enhance, to improve the amount of phosphorus to recover, but also to prevent uncontrolled struvite precipitation in the installation. So the sludge is coming from all the treatment plants and also from the belt thickeners of Amersfoort. And then the sludge is dewatered in the belt press. Oh, too fast. In the belt press thickener before it ends up in the digestion tank. Then we move to the gas phase, the biogas phase. So we produce a lot of biogas in the digestion, but it is improved by the thermal pressure hydrolysis reactor. What's new in this scheme is that normally you have the hydrolysis before your digestion, and here we have it parallel to the digestion. And we were a little bit afraid that it wouldn't work, but they promised us it will work, and today we see it works well. Yeah, it looks like this. I'll show you later outside how it is in reality, but it's some pictures about the lysotherm and the gas storage. Some details about it, and then I move on to the Struvite reactor, the pearl reactor, and I'll give the floor to Derek Leike to explain a little bit about that.
Thank you, Henry. So the slide up here right now is depicting the pearl crystallizer reactor. In chemical engineering speak, this is an expanding upflow fluidized bed reactor. It's expanding because it's narrowest at the bottom and it's widest at the top. And it's upflow because all of the feed comes into the bottom of the reactor. And that feed is your nutrient-rich wastewater streams. So that's the dewatering liquor off the anaerobic digester. And in the case of applications such as Amersfoort, it's also the wash strip stream, which is a pre-digestion phosphorus release stream. So those two, that nutrient-rich wastewater combines with magnesium feed, a soluble form of magnesium at the bottom of the reactor, since we don't have quite enough magnesium in that feed stream to precipitate all the phosphorus we want to. It also combines with chemical for pH control, such as sodium hydroxide. It combines with a recycle stream coming from the top of the reactor. And that recycle stream is depleted in nutrients because all of the reaction has been done by the time it gets to the top. And it adds to the fluidization properties of the reactor, allowing us to control the size of the particle we make. So because it's an upflow reactor and because it's expanding, it creates a velocity profile in the reactor where we have the highest velocity at the bottom and the lowest velocity at the top. That means that as the struvite prills, as we call them in the fertilizer industry, grow, the heavier ones fall to the bottom, and when they get to the size we want, we can harvest them out as a finished fertilizer product, and that STOWA markets as crystal green. So we're not finished there, obviously. When it comes out of the reactor, it's entrained in liquids, and we have a small fertilizer manufacturing facility right here on site that dewaters the product, dries it, and then sorts it into relative size grades. And the end goal of every one of these facilities, and there are 14 of them worldwide by the end of this year, is to produce crystal green. I forgot that I had a slide of photos here, so I'll go through that quickly. On the left there, you've got the pearl reactor, or at least part of it. You'll see a better example of that on your tour today. Top center is the dryer, so it's a fluidized bed dryer that dries the product. And below that is a sorting sieve to sort it into its different size grades. Primarily, we target one size grade, but we do get some overlaps with whatever's on top and bottom, so we want to classify it into the sizes required by the fertilizer market. And then on the right-hand side, finally, we've got the bagging system where the final product leaves the site. And that final product is crystal green. Every STOWA facility that operates around the world produces that same product to a certain specification. It is a slow-release fertilizer product, struvite-based, obviously, and comes in 4 different size grades as required by the fertilizer industry. That size grade number, as they call it, is essentially the diameter of the particle in millimeters times 100, And different applications of fertilizers require different sizes because they blend it with other fertilizers of nutrient value in order to make a finished product. Turning back to Henry now. Thank you,
Derek. Yeah, so just the overview of the installation again to have an idea what's what. So the gas storage, digestion, the pearl reactor, the crystal green storage, the wash strip reactor and the lysotherm. And at 4 o'clock we have the possibility to show you the installation outside. Yeah, so few slides only. So what we at this moment found out is that we have more biogas produced than expected, so that's hopefully. As I already said, the biological peer removal, phosphorus removal has to be still to be improved, and the sludge dry weight is still increasing, and we hope to end up above 30% dry weight. As I already told, we are working on sludge drying with the access heat of this installation, and this the installation in Ede, where we are doing a pilot now. We're just starting it up, and hope to learn a lot of about this technology. We will operate it for 5 years, hopefully, and then in between hope to translate the results to Amersfoort or other plants in the Netherlands. Yeah, and then besides just talking about phosphorus and energy, we're also thinking about clean water, of course, phosphorus nutrients, or nitrogen, alginates. We're working on alginate plant in the eastern part of our installation, valuation of biogas for transport, carbon dioxide. So there are a lot of possibilities nowadays to improve our treatment plant and to make it a sustainable treatment plant and to produce nice products. And we're also working on concentration of wastewater to make it all possible, especially because we have the next challenge to remove micropollutants from our wastewater. And actually it's too diluted now to do that in an efficient way. Just a nice picture of the energy and resource factory, the Dutch energy and resource factory, the program, to show you what all the possibilities are. That's my presentation. Thank you.
Thank you. Maybe stay for a little while. Are there any questions?
My name is Michael Schuller from Trion Puritech Consulting and Engineering. And my question is, what is the size of the pellets produced in the pearl reactor?
Derek, can you?
So the target of those sizes are anywhere from 0.9 millimeters in diameter, 4.5 millimeters in diameter, and that's the range that fertilizer blenders and distributors will use to blend with their existing products. Just to give you an idea, the smaller range would be used in greens, so things like football fields, golf courses, and the larger sizes are used by the agricultural industry.
And another question, and what about, so how much struvite is in it? Is it?
It's virtually 100% struvite. I think we say 99.6%. The only thing that you might get is some minor amounts of calcium phosphate precipitation, but we operate at such a low pH that that's not usual at all.
Yeah, my name is Hans Geers. Henry, you showed us a payback time of 6 to 7 years. Is it with life subsidies or the total cost of the investment?
Yeah, so it's about 1 or 2 months difference, because the life is especially the life funding is especially for things like this, sharing the knowledge, and but part of it is lucky for the installation, also for the let's say for the sludge drying installation. To make it clear, if we had not have the life funding, we would not have built the sludge drying installation. It has cost so much effort to realize that within the day-to-day operation. And the same for the phosphorus removal. Yeah, that's an extra, let's say, support to do this. Yeah.
Are there more questions? Maybe here? No? Ah, go on.
My name is Cora Uiterlin from STOWA. Omzet Amersfoort is a very nice example of the energy and resource factory. What would be the next step of Amersfoort? Do you think it will be the removal of the pharmaceuticals, or do you think of other resource compounds? What would be the next step in 10 years, 15 years?
Yeah, we first need 7 years to pay it back. So, but I think the next step will be at other places. So we are, for example, working on a treatment plant in Wilp, where we try to build the installation of what we call 2030, removing cellulose, producing clean water for real clean water for KRW surface water. Kind of like, yeah, what we like to, besides the sludge drying, is to improve the water quality, but not at Amersfoort, but at some other sites of the Waterboard. Yeah.
More questions? No? Henry, you said that you there were no real failures. You couldn't share anything about it. What was the most difficult moment in this whole project, in the realization of this beautiful installation?
The most difficult one is to let's say to get our board within the project overtuigen, convinced our board to that we should do this, because we had a lot of risk to build this. Yeah, that's it actually. And of course, there were also some technical things, but we think that the market parties who build this are able to do this. So that was not a problem.
And how long of these 8 years was it to convince the board?
About 3 years.
Okay, so in 5 years you can realize such a beautiful resource recovery plant.
Yeah, of course, yeah.
Okay, good. Well, thank you so much for your interesting presentation.